we looked at functions of two variables, integrals of a function of two variables along a path in its domain. And the things we integrated were these linear differential forms. Okay, which were these expressions, kind of generalization of a differential form that you integrate from one variable, so it's some function p of x and y times dx differential plus qx of y times the dy differential. We looked at some examples of how we evaluate these. Okay, and there's a little example there at the end about calculating the work done when a particle moves through a force field. That's an application from physics. But today we're going to go on to look at another type of integration, double integrals. Again, we'll focus on functions of two variables, but these concepts do generalize to functions of more than two variables, and indeed we'll see some examples of integrating functions of three variables and so on in due course. So this is different to integrating the function along a curve in its domain. This time, so the domain of the function is R2, okay, so it's a function of two variables. So this time we're going to integrate across a two-dimensional region, some two-dimensional subregion R, which we're going to call R for the moment, R of the domain. Okay. So there's a bit of a sketch here, figure 1.5. So figure 1.5, so the gray portion at the top is a portion of the surface defined by the function z equals f of x and y. We think that the domain of the function as being the xy ground plane and z being the vertical axis. And under those conventions, the function defines this surface in three dimensions. Okay? At any point xy over the ground plane, the height of the surface over that point is given by the value of the function. So depicted here, the surface is all above the line, so this function is positive on these over this part of the domain. So we're going to look at objects like this in equation 163. There, it's a double integral, so it has a double integral sign. It's over a two-dimensional region, and we have the two differentials, dx and dy. Okay. So one way of thinking about what this represents is this represents, so it has a very clear geometric meaning, geometric interpretation. This is going to give you the volume of this kind of this tower that's depicted there in figure 1.5. So it's going to give you the volume of the space that lies over the region R, the kind of cylinder, straight sides over the region R, and the top portion of the surface of the top boundary of the volume is provided by the surface itself, the surface defined by that. Okay. So we're talking about the volume lying in this little tower shape. Now it looks kind of boxy, but in general, the region R won't be a nice rectangle. This region R on the xy plane in general could be any two-dimensional subregion of the plane. And then this double integral is going to refer to the volume of the cylinder over that plane. Okay? So when you take that region R and consider the volume defined with R as the base and the surface defined by F as the top boundary. And it's got straight sides coming up from the region R up to or down to wherever the surface is. So this is, you can think of this as well as being a nice generalization of the integrals of functions of one variable. Okay? There we have the curve defined by the function. We integrated over a sub part of the domain, so we integrated across an interval, a to b, say. And the integral had a clear geometric meaning. It meant the area between the domain, between the region in the domain and the curve defined by the function. The area under the curve, as it's commonly said. Well, this is just bumping everything up in dimensions by 1. Okay, function of the dimension. So we're now integrating over a two-dimensional subregion of the domain, and the integral gives us a value. Okay, well, how are these things actually evaluated? Well, they're also called repeated integrals, or at least the form of the expression in equation 165 there is a repeated integral. So it's one integral nested inside the other one. Okay? So here it's written as the dx integral on the inside. Okay, now we're picking up some of the notation from 1.5. So this rectangle goes from a to b on the x-axis and c to d on the y-axis. So this double integral over the region R can be expressed as this repeated integral, where we integrate from a to b the function f of x, y dx, and then in turn integrate that integral from c to d with respect to the variable y. Okay. A similar principle, the similar principle is in play here that we used when we were performing partial differentiation. When we were taking partial derivatives of a function with respect to one of the variables, we treat any of the other variables of the function as if they were constants for that purpose of taking the derivative with respect to this other variable. It was a very similar thing in integration. If you're integrating with respect to some variable, so this inner integral here, integral a to b of f of x, y dx, this is integrating with respect to the x variable. So any other variable, namely y, that appears in the expression for f, is just treated as if it were a constant. Okay? So it takes part in the integrals of any terms involving x, just as normal, and then the integral would get evaluated at x equals a and x equals b, and so on. Okay? So this inner integral, we'll do an example now. We'll do example 1.18. That inner integral, it should be recognized as a function of y. So let's look at this. So it's preparing, for example, 1.18, excuse me. So when we think of it as the double integral, this whole inner integral will in general be a function of y. Good to see they fixed the visualizer. In fact, they've given us a new visualizer over the old one. That's pretty good. So some of you commented in the staff student liaison committee that the visualizer was bad. So we've got you. Okay. You see that inner integral there removes all reference to the variable x. After you've done the integration and you perform the evaluation at x equals a and x equals b, so these are limits for the x variable, remember, and these are limits for the y variable. You can tell which variable they're limits for by looking for the matching differential. Okay, so this integral is matched with this differential dx, so these are limits for the x. Normally we don't write x equals and y equals here, but I'm just doing it in this first example just to be explicit and just to remind you. So when the inner integral is completed, all reference to the variable x will have gone. Okay? Because we'll have made substitutions for x, at x equals a and x equals b. But in general, if there was any reference to y in the function f to begin with, that reference to y will still be there. Okay? Yeah, presumably, as long as it hasn't been cancelled out by the evaluation of x. But in general, probably it won't. Okay? So in general, this inner integral is going to be a function of y, but then doing the outer integral, that should remove all reference to y then, okay? Because you're integrating with respect to y, and then you're ending up by evaluating at two boundary values of y. Okay? So this should just come to a number. This should evaluate to a number. Okay, so let's have a look at this example. So for this particular example, we're given the function f of xy, which is 2xy plus 4x plus 3y plus 1. Now, I mean, it's more or less there in the notes. Yeah, let's just talk through it. So here we're dealing with an integral I, which is, well, we'll sketch the region R. So the region is between x equals 0 and x equals 2, and y equals 1 and y equals 3. We've got 1 and 3, and we've got 2 here, so we're talking about this rectangle. So this is the region R. It's the x and y axes. Sorry, 1 and 3, sorry, oops. R only consists of this bit, sorry. Y is between 1 and R. So it doesn't include this, the bottom portion, so here's a better picture of it. Okay, so that's the region R we're integrating over. And here. So we're going to integrate with y on the outside, so from 1 to 3 and 0 to 2. The function we're doing is 2xy plus 4x plus 3y plus 1 dx equal. So this is interpreted as a pair of nested integrals. We've got the x integral, drawing the brackets can help separate it. We've got the x integral inside the y integral. So to evaluate this, then, well, the y integral operation is still there on the outside, integrating from 1 to 3 dy, but we're integrating the middle part with respect to x. So we treat the variable y as if it were a constant. Okay? So this becomes x squared y plus 2x squared plus 3xy plus x. And that needs to be evaluated at x equals 0 and x equals 2. Now at this point, before you do this evaluation, when you're doing this the first few times, just be careful. These are limits for the x variable. So we're substituting in 0 for x and 2 for x when we're doing the evaluation. So we evaluate it at x equals 2, and then we subtract the evaluation at x equals 0, just as we normally do with integrals. But you don't go substituting these values 0 and 2 in for the variable y. Y is just treated as a constant for the purposes of this x integral. So what do we have multiplying y? We'll end up with 4y plus 6y. That will give me 10y in total if we evaluate it 2. When you evaluate at x equals 0, you don't get any y's because they get cancelled out. And there's a constant term. When you evaluate at x equals 2, we've got 8 there plus 2, that's 10. Yeah, so that agrees with what's in those. So that's the evaluation done. So you can see there now that what we've ended up is 10y plus 10. So all reference to the x variable is gone. If we've integrated it out, it's the expression that's used. We've performed an integral with respect to x, and we've substituted various x values in, taking the difference of those evaluations. So all reference to the x variable is gone. If you reach this stage and you've still got an x appearing here, that points to that you haven't done something correctly along the way. Okay. So this now just looks like an old familiar one-dimensional integral that we integrated without too much bother. So we've got a 5y squared plus 10y, and then that needs to be evaluated at 1 and 3. So it's going to be 5 times 9, 45 plus 30. Minus 50. 60. Yeah. Okay, so this 60 has an interpretation. Okay, so the volume between R and the surface z equals f of xy, and 60 cubic units. Be a little bit careful, because just as with one-dimensional integrals, any portions of the surface that are negative, that lie below the horizontal plane, the volumes there between the region and that part of the surface, they'll have a negative contribution to the overall area. So they're kind of like sine volume. So any portions where f of xy is negative, these contribute a negative volume contribution to the integral I. Now, just while we're on this example, there's nothing special about the order in which we perform the integrals. We had the x integral there as the inner integral, and the y integral as the outer integral. Well, just as well, or just as valid, we can change the order around. Okay? So I could also have been evaluated as, well, with the inner integral with respect to y this time, and the outer integral with respect to x. Of course, you still have to bring the correct limits and the correct integral signs. Okay. Now, this is something important to discover that. I mean, looking at it some ways, perhaps this might give you a different value when you do the integration in the other way around, but it shouldn't, because of this interpretation of the double integral as being the volume lying over the region and on the surface. Then this integral, should just give you the same volume. Okay, we're just taking the variables in a different order. So here you'd be left with integral 0 to 2. Now integrating this with respect to y now, it becomes xy squared plus 4xy plus 3 over 2y squared plus y. And that has to be evaluated at 1 and 3. And after doing that, you can integrate the result with respect to x. So you have 9x plus 12x. 9x plus 12x will be 21x. And constants here, you have 3 over 2 plus 1 is 5 over 2, so the positive part. And then the negative part is x plus 4x, so the negative part is 5x. And 3 over 2 and minus. That would be minus 5 over 2. Yeah. So it's still plus 5 over 2. So that cancels. So the integral 0 to 2, 21x minus 5, so 16x. Just 16x. It would appear. If I haven't made a mistake, this integral will be integral 16x will be 8x squared. Evaluated 0 and 2. Oh, I must have made a mistake somewhere. That doesn't evaluate 60, that evaluates to 8 times 4, which is 32. So where did that go wrong? So when you put the 3 in, well, let's make sure it started off the right way. 2xy plus 4x plus 3y plus 1. Xy squared. 4xy. 3 over 2y squared plus y. Sorry, this was wrong. This 5 over 2 bit was wrong here, wasn't it? So when you put 3 in, you get 27 over 2. Yeah. Put 9. So 27 over 2 plus 2 over 2. 27, so it gives you 29 over 2. So 29 over 2 minus 5 over 2, so that's 24 over 2, which is 12. So this is 8x squared plus 12x evaluated at 0, 2. So 32 plus 32, 8 times 4 is 32, 24, still have 60 here. Half of 24 is 17, isn't it? 24 divided by 2. It's what? That's 12. Everybody see where it's gone wrong?
2902.
Sorry, that's it?
It's 2902. Real 2. Like 202 instead of 602 to the y. And like get that 1, 3, 1 instead of 3.
Oh, but it should have been not. So when you substitute in 3, you have 9. 9 times 3 is 27. 27 over 2. 27 over 2.
Yeah.
Why did I write down?
3. Yeah, 202 to 602. 2902.
29 over 2 plus 3, and 3 is 6, so 29.
So 27. Like 27.
27 plus 6. So 33. 33.
Yeah.
All right. Okay, so you can see the many traps, of course, here. And then 33 minus your 5 is your 28. That seems a bit better. 28 over 2, which is 14. So that's 32 plus 28, which is indeed 60. Phew, thank you. Okay, but, you know, so I knew I was going wrong somewhere because I wasn't getting the same answer as I got before. Okay, because changing the order of integration does not change the value of the double integral. Okay? However, as we'll soon see, changing the order of integration when the region is not rectangular, that has to be a lot more care is needed there. So changing order of integration when R is not rectangular needs careful handling, as we'll see shortly. Now sometimes this changing the order of integration can make quite a difference in how easy it is to carry out the integral. Okay, so this is the next example, example 1.19. We have a look at that now. So here we're tasked with performing this integral, 0 to 1, 0.2 to 0.8, say x times the cosine of xy dx dy. Okay, we can recognize the region is rectangular because the 4 limits of integration are just constants. So x just varies between 2 constant values and y just varies between 2 constant values. So that's describing a rectangular region. But if we were to perform the integral as it's described there, the first integral we'd have to do would be integrating x times the cosine of x times y. That's not a possible integral to do, but it's going to require integration by parts. Because you've got a product of two different, two functions of x. So often it can be easier to change the order of integration first. Or when faced with an awkward double integral, it can be a good thing to try changing the order of integration. Because when you look at the integral this way, suddenly it's easier to make progress, okay? Because we don't need integration by parts technique to handle the inner integral next. It's just an integral with respect to y of x times the cosine of x times y. So we just treat x as a constant. Treat x as a constant, and then this suddenly looks a bit easier. It's just sine of x times y. That gets evaluated at 0 and 1. Okay, so this was changing the order. And this was an easier integral than above. An easier integral to do than what it looked like at first. Okay. Now you can do the evaluation at 0 and 1. So this will just be integral 0.2, 0.8 of sine of x. Remember, these are limits for the y variable. The sine of x minus sine of 0, but sine of 0 is sine of 0. So it just reduces now, you can see, to straightforward one-dimensional version. Okay, which has whatever value it has. So often changing the order of integration can sidestep some difficulties in the integrals. Another, so just before that example in the notes was the issue of separable integrals. These are double integrals where the function, or when the integrand factors as, so you start off with a function of two variables, but if it's possible to, g of x, h of y, if it's possible to factorize that, so to take all the dependence on x into one function and all the dependence on y into another function, and if f is just simply the product of those two, it factorizes into everything to do with x times some other expression which is everything to do with y. If that's the case, when that happens, the double integrals factorize as well. Because a repeated integral of fxy dx dy with limits, so this is double integral gx times hy dx dy. This is a repeated integral now, but remember, when you're integrating, so this inner integral is with respect to x, when you're integrating with respect to x, the function h of y, well, y itself is just treated as a constant. So the function h of y, whatever it is, will just be some other constant. And a constant multiplying a function of x, which is to be integrated with respect to x, that can be simply taken outside. So there we're factorizing the hy outside of the inner integral. But now the inner integral is just an integral of a function of one variable with respect to that variable, integral of g of x with respect to d of x. So in particular, if we have limits, we have some limits, this will just be a number. But even if we don't have limits, then if we don't have limits, this integral here is independent of y, because it doesn't mention y. G, by description, is just a function of just the variable x. You're integrating with respect to x, so there's no reference to y there at all. So in terms of this outer integral, in terms of this outer y integral, the inner one is just treated as a constant. Okay? It has no dependence on y, so it can move outside as a whole chunk. It can move outside the y integral. Factorize it out of the integral like this. So you're left with just the product of the two integrals, as it's written in the notes. But I put in a few intermediate steps. So if your function factorizes into a factor with all the dependence on x, and the other factor with all the dependence on y, then the same thing will happen to the double integrals. Okay, any queries at the moment, or anything I could clarify there? Okay, so we'll go on now to look at the, see, all that is really a special case of when you have rectangular regions. We'll want to look at the more general case now of when you've got non-rectangular regions. Okay, this is section 1.16. And the main point about these is, well, being able to recognize them when you encounter them, and also being able to change the order of integration correctly. So it's best to look at an example. So in figure 1.6 here, well, we can see a non-rectangular region. So we're going to integrate this function f of xy, 4x cubed plus y cubed. Now the function isn't indicated here. Here we're just indicating the region. So the description of the region is that part of the plane that's bounded by these are three curves. Curve x equals 2, so it's a line parallel to the y-axis. The line y equals 1, which goes parallel to the x-axis. And the curve y equals x squared. So you can see y equals x squared there, drawn at the origin coming out. So this gives this approximately triangular region. The horizontal and vertical sides are straight, but what would be the hypotenuse there is actually the curve y equals x squared. So it's not exactly a triangle, but it's roughly triangular a bit. So first of all, we have to decide, or we have to indicate how we're going to represent or how we're going to evaluate the double integral over this region. Okay, well, you can see it's through the use of, well, you recognize the fact that this is a non-rectangular region. This is recognized in the form of the integrals written down because one or more of these limits are non-constant. Okay, so you see the inner integral here with respect to x, one of the limits is a function of y. So as soon as you see functions of the variables appearing as limits of the integrals, then you know it's a non-rectangular region. Okay? These functions of the variables that appear in the limits, these are actually the defining functions of the boundary curves expressed in the appropriate way. So we've got this double integral here, and I will just talk about this on the board a little bit because it's partly the explanation for this is the way you write down the limits, the order in which you write down the limits. So example 1.20, doing the double integral over R of 4x cubed plus 4y cubed dx dy. Now the first thing that's done is just a decision to make the inner integral be the x integral. Okay. So this is our decision here. We've decided that we're going to, we want to express this integral with x as the inner integral and y as the outer integral. So then the question is, how do we decide upon the limits? Well, kind of general tip here is for the limits of integration, work from the outside in. All right, yeah. So the outer integral we see is the y integral. So we look at the region, so you can look at the sketch, and this is why it's a good idea to sketch these regions as well. Looking at the region in figure 1.6, we ask ourselves, well, over what values of y do we need to integrate in order to integrate across the region R? Well, you see, the region R there extends from y equals 1 up to y equals 4. There's no parts of the region outside of those limits between y equals 1 and y equals 4, but everywhere between y equals 1 and y equals 4, there's a part of the region. Okay? So that tells us that these limits should go from 1 to 4. So from y equals 1 to y equals 4 is the extent of the region R against the y-axis. But then when it comes to the inner integral, okay, we don't just go, you could ask a similar question and you could say, well, where is the region with respect to the x-axis? Well, there's part of the region at x equals 1, that bottom left corner of the triangle, so to speak, and the region goes up to x equals 2. Now, if I just put in x equals 0 and x equals 2 here on the inner integral, it won't be over that region R, it'll be over the whole rectangle, from y equals 1 to 4 and x equals 1 to 2. But we don't want to integrate like that. We just want to integrate over the triangle. So here's just a quick sketch of the triangle. It's curved hypotenuse. We think of the y integral on the outside as supplying a typical y value. So the outer integral supplies a typical y value somewhere in the range between 1 and 4. And then you ask yourself, well, how much of the, what does the region look like at that y value? Well, at that y value, you see, the region isn't extending from x equals 1 up to x equals 2. Okay, so we're kind of halfway up the triangle. But what is always true is, no matter what y value you're talking about, the region does always go all the way up to x equals 2. So it's always the case that we need to integrate up to x equals 2. But where we start the x integral, well, that changes because it depends how high. When you're down near the bottom of the region R, you're going from close to 1 up to 2. But when you're getting up near the top, you're just integrating from very close to 2 up to 2. So what are these values? Well, these values, they're determined by y. And they give you these values here on the x-axis, and the value they give is the square root of y, isn't it? Because the function describing this curve is y equals x squared. So if the outer integral supplies this intermediate y value, corresponding starting point for the x integral is the square root of y. So that explains why this lower limit here is the square root of y. So it comes from that square root of y there. This comes from, the hypotenuse like thing, which was originally defined to us as the curve y equals x squared. But it's been turned around here because of this decision to make y the outer integral. Now this will have a certain evaluation. You can see it in the notes. I won't go through it on the board again. But once you reach this stage, you can just proceed with the evaluation as we have before. The only difference is that you've got a non-constant limit of integration. You just handle that in the same way. So you can see down at equation 182 on page that is. Page 31. The inner integral with respect to x is being carried out. We get that expression x to the power of 4 plus 4xy cubed. And that needs to be evaluated at the limits 2 and square root of y. And those are limits for the x variable. Remember, this inner integration with respect to x, this has to remove the x variable when you're done with the integration. And you do the evaluation of the limits. So putting in x equals 2 and subtracting the expression from x equals the square root of y leads us then to that polynomial in y you see there on equations 183 and 184. Then you're down to just an integral with respect to the integral of a function of one variable that will be carried out in the usual way. Okay, but we'd also like to see this the other way, which is to say, see it as the inner integral now with respect to y, the outer integral with respect to x. How would that appear? Well, I mean, you can see how it appears in the notes there, just at the end of the example. But we can arrive at the limits by following this same principle at the top, from working from the outside in. So now we look at the region R. Now we look at the region R, and we first, because x is the outer integral, we first ask ourselves, well, where is the region with respect to the x term? And it's got just a simple answer. Well, it goes from x equals 1 up to x equals 2. Okay. There are parts of the region at x equals 1, and they go all the way up to x equals 2. Now to come to the y integral in the middle, we imagine the outer x integral supplying an intermediate value of x to the inner integral. Okay. Because the inner integral, remember, is a function of x. The inner integral is a function of x, as I told you before. Now, where are we integrating with respect to y? So at that value of x, now we picture a vertical strip. And at other values of x, we have other vertical strips going through the region. These are the ones we want to integrate on. Now you see here, they all begin at y equals 1. So y equals 1, we've got a simple constant limit, lower limit for the y integral. But the end point of these vertical strips is not unique. That changes. And of course, if we're talking about the vertical strip at a particular value x, the y variable along that strip just goes up as far as x squared, okay, because that's the definition of this curve. So that's why we're integrating from 1 to x squared. Okay, so there's a definite procedure or flow or order in which we arrive at these limits of integration. It's so easy to get across on the printed page. But now, having got it to that stage now, this describes the double integral over this region R of this function 4x cubed plus 4y cubed. So this can be evaluated now using the same techniques as before. Only just be careful that you've got a non-constant of integration there, but that can just be handled the same way. So that x squared there at the top of the inner integral, when you do the inner integral with respect to y, that x squared will go in, be substituted in for the variable y in the integrated expression. So you'll end up with, when you do the evaluation of x squared, subtract the evaluation of x at y equals 1. Then inside this bracket here, you'll have an expression with respect to x, which then gets integrated and evaluated over 2. So again, it brings you to this number 745 minus. So this should give, and of course, both orders give the same integral. Okay, but if you're just starting, I mean, if nobody told you about the region, if you were just faced with this first integral just on the page, and you wanted to change the order of integration, maybe to make the integration process easier, it's not immediate, it doesn't scream out at you that when you change the order, it must be from 1 to x squared. It's not immediately obvious. So it certainly helps, or I think this is the only way to do it, really, to be fair, is to go via a sketch. So you sketch out the region that's described by these limits of integration, and then that will, by talking about these vertical or horizontal strips, then you'll be able to decide on the other order, and then go through and actually decide what the limits of integration. Okay, so for the tutorials, you've certainly got plenty of stuff here to be working on. On page 30, you've got exercises 1.6. They're all on double integrals over rectangular regions. And on page 33, well, the first two, I think you can do the first two there, questions 1 and 2. The other question, and I'll give you some more on these, I think, so you need some more. Those are based on this idea of changing coordinates, which we'll do next time.